All right, we are gonna just kind of continue and finish the notes today. The first thing I'm gonna put up here on the PowerPoint is actually just kind of a little bit of a repeat from before. I liked some of these bell ringers here, so I wanted to use them real quick. If a negatively charged particle, actually, hold on, is the positive one? I want to do the positive one first. I thought you're going the wrong way. What are you doing? Stop it. Stop it. There it is. Okay. Yeah, this is right. Okay. So, in a figure below, there's a graph of an electric potential as determining by position. So if you want, like, imagine just a straight line x, okay, and these numbers of potential talk about energy, okay? So what we have discussed in this particular case is what potential should do. Well, what should potential energy always do? Decrease, okay? So for a positive, you'll remember that potential, well, not for anything potential. Potential is defined as potential energy over Q, right? So what you want to think of here is that when you think of V, potential energy is just Q times V. Yes? Meaning, when I say for a positive, you look at this and go, oh, for this potential, okay, positive means all these numbers up here are positive. Fair? Okay? So when you look at this, you should go, all right, as I look at this, positives should do what in this particular case? So in here we say, all right, you have a particle placed at position B in the figure below. It's given a very small kick to the right. What should its subsequent motion be? What should potential energy do? Decrease. So what should a positive do if kicked to the right? What do you got?
Point A is positive.
What's that?
Point A is positive.
What do you mean it's positive?
Is point A a positive charge?
And there's one positive charge in this. Point A is a position and the potential energy of it. So this location is the potential energy, the potential, electric potential, compared to that. All right. Let me paint this picture in a different light that I think will help. Potential is like the measurement of an empty hill. Instead of looking at that graph right now, imagine this as a hill. What's a positive going to do on that hill if kicked to the right? It's going to go right. It's going to stay decreasing in potential energy. So the answer to this one is number 1. Okay? Now the thing you have to consider for number 2 is let's do the exact same thing again, but consider a negative. Now when you do that here, you go, oh, what does that mean the potential energies are doing? Well, now for the same potential, the potential energy is negative. Meaning, if I say a potential is 400 volts, and this is 0 volts, if I put a positive in here, which of the two is more likely? 0, because it's smaller, right? But if I put a negative in here, which position is more likely? Negative 400. Okay? The way you should look at it is based on our definition that we've discussed. Electric field points from a high potential to a low potential. Okay? And potentials don't know, they're not positive or negative inherently because they have no idea what other charge is being put into them yet. Does that make sense? So if you kind of keep track of this type of idea in your head, that it goes from high potential to low potential, you can start to get that, oh, that means positives naturally would go towards that 0, but negatives would naturally go towards the 400. And the reason it goes towards the 400 is once you start to talk about potential energy would be that for a single coulomb, that's that 400 joules, 0 joules for a positive, negative 400 joules, 0 joules for a negative. Does that make sense-ish? Let's go back here then and answer this question. So now you've got the same situation. We have a charge that's placed at B and given a very small kick to the right. What should it do?
1.
No, that's what a positive would do.
A and B.
Well, you just kicked it to the right.
Should go to the left.
Should oscillate around point B. What you want to kind of think of it like as is I just showed you this picture and said for a positive, imagine this as a hill. Okay? Now, for a negative, what you do is you kind of invert that 108, like you just kind of flop that. For every hill, it's now a valley. So, if you will, for a positive, you can kind of think, hey, there's a positive on top of this hill, it's going to roll down the hill over there. Or in terms of energy, the potential energy is going to get more and more negative, it's going to keep going. For a negative, kind of like flip it, or think of it like this. Now, instead of kind of gravity going down, as it were, imagine gravity going up. And so that negative is no longer on a hill, it's in a valley. And so if you kick the negative and it goes over here a little ways, what's it going to do in that valley? It's going to oscillate back and forth. Now, in terms of energy, the way you should look at this, once again, is that this higher potential is a lower potential energy. Hear what I said just there, because I know they also the words kind of run together. The higher potential is the lowest potential energy up here. How are we doing?
Just need a second break. You should know what it is.
Already.
I don't know.
Sure. Thank you for checking. I appreciate it.
Hello, Morgan.
So you're saying the higher the potential, the higher the change in potential energy?
So it just really goes back to the picture I just showed. A high V, the electric field points to a low V. Okay? But potential energy can swap on these depending on what's in there. And if you remember this, that electric field, you can kind of follow the rules that we already know, right? What does a positive do in an electric field? As a push in that direction. So which way would you expect the positive to go? You'd expect it to go to low potential. And that matches in terms of energy, because when you use energy equals QV, that's a positive and that's a positive. So like this, what's the example I was using before? So I'm going to use some slightly different numbers. So I'm just going to make sure, say this is 10 positive joules, and this is, say, 6 positive joules. Okay? So what do we expect in terms of energy? We expect the energy to decrease. We expect it to naturally go that way. Whereas, if I put a negative in there, because this is now negative, these are still going to be the exact same numbers, but now that's -6 and that's -10. So if we come and look at this electric field, once again, what do you expect a negative to do in an electric field? In this case, you'd expect it to go left. So you'll notice that this technically, the negative will go from a low potential to a high potential. But that's not necessarily the way you want to think about it. The way you want to think about it is, if I put a negative up here, I get -6 and -10. So you think about it in terms of energy. What do all objects want to do in terms of energy? Decrease potential energy. So decreasing for positive was moving from 10 to 6. Decreasing from negative is moving from -6 to -10. And if we go back to this example real quick, back over, would you stop pushing the wrong direction? For the positive, if I say it kicks right, is it going to keep decreasing potential energy forever? I mean, according to this picture.
Yes.
You get to keep decreasing energy, at least as far as the graph is concerned, all the way down there, which is why it goes right and stays going right. In terms of the negative, notice, by the way, in terms of the positive, potential energy is, electric potential is decreasing. Exactly what we said here, that positives should go towards that low potential. But what should negatives do in terms of potential? Go to the highest potential, because the highest potential is the lowest potential energy. And what's the highest potential on this graph? here. But if you think about it in terms of a valley, the reason it doesn't oscillate here is because it would pick up a little bit of potential energy going uphill, just like a hill would. So why won't it stop when it comes back? Because the potential energy will convert back into kinetic, so it's moving, so it's not going to stay here. It's going to come back and come and oscillate back and forth. Now, actually, if that actually does happen on this level, that's infinite. Okay, assuming that everything stays the same. Unlike in our level with a hill, it's not infinite because of if you drop a ball into a valley, why is it not infinitely going to go back and forth on our level? Friction, correct. No friction on this level because we're talking literally about the stuff of friction. Good. Electric potential. No. All right. So, battery in a car. What would you expect its electric potential to be? What would you expect? Just maybe some of you know. What's the answer? 12 volts. Little bit surprising, yes, because can you get a 12-volt battery that is this big?
No.
Yes, very much so. You can get a 12-volt battery this big. So what is the difference then between a 12-volt gigantic thing and a 12-volt here? Well, in that particular case, again, think of it like an empty hill. These two hills, the 12-volt that I'm, the tiny one that I'm fake holding in my hand right now, and the 12-volt in the picture, are the same size of a hill. That one lasts a lot longer. Why? In terms of physics.
More space. 12, 9 volt. No. More space.
Use my analogy of the hill. In the empty hill analogy that I use,
There's more hill
what?
to fall down?
Not quite. Nope, the same size hill. Like we said, 12 volt.
Steeper hit.
So let me help you. Okay, here we go. 12 volts means what in terms of electricity? 12 joules per coulomb. In my empty hill analogy, 12 joules per child. Correct. So, are the hills the exact same size? Yes. So what is the difference between the giant ass battery here and the small fake one in my hand right now?
That one's scarier, going back to the example.
It can
of how
generate
somebody
more
was
children.
skilly, I
What's
don't
that?
know.
Can generate more children.
There are
Has
more children for that one. There are more coulombs in that one. So are they going to put out the same amount of energy per coulomb per child? Yes. However, this one's going to last a lot longer because more kids. Sorry, more coulombs. All right. I talked about this the other day, so I'm not going to do it again. Essentially, this is the graph like I was talking about. This is the potential right here. That's the equation you're using when what? When do you use this one, and when do you use this one?
Oh, what charges on
Point charges is the right one, and the left one is
uniform?
uniform electric field, correct. Okay, moving on. Went the wrong way. Superposition principle says the total electric potential, this is what we talked about yesterday, but the total potential at a particular spot is just a combination of all the individual ones. This is a two-dimensional thing. Essentially, this is just a two-dimensional hyperbolic graph that says the exact same thing. Okay, these are electric potentials in two-dimensional space if you have a positive and a negative right next to each other. In other words, you can better visualize what is a positive going to do if it's put right here. Well, you're going to see that it's going to lower its potential. It's going to come down, and if it ends up over here, it's probably just going to go that way, more than likely, just like in empty space. Now, is this location more likely than that one? Sure. But if it's already headed this way over here, is there any reason to drop down into that over there? In the exact same way as we've said in this classroom, the ground is definitely the more likely place to be, but does that automatically mean it's going to end up on the ground? No. You have plenty of things on the desk right now. There's plenty of things on top of my desk. It's pretty messy. Anyway, so it's not necessarily going to end that way. Now, that being said, if the positive starts over here, it's definitely going to go there. Okay? Now, that's for a positive. But, sorry, I screwed up, by the way. Did I? Yes. Yeah, no, I didn't. I'm good. Okay? This would be a positive next to a positive, right? If a positive started down here, is it probably going to go anywhere? No. In terms of energy, it's at its lowest energy. But in terms of just kind of understanding this, this is created, like I said, by a positive here and a negative here. So why wouldn't it go anywhere if it was there? It's right next to the negative. So what do positives and negatives do? Attract. Are they going to do any work if they're just sitting here right next to each other? No, absolutely not. Now, is a negative going to follow that same path? No. What's a negative going to do? In terms of potential, the negative is going to do what? It's going to go opposite. It's kind of, if you want to think about it in terms of gravity that you're comfortable with, okay? In terms of gravity, gravitational points down, and we expect mass to go down. If an electric field goes down, we expect positives to go down. So you can kind of draw an analogy to think that like positives work like normal gravity would. Okay, negatives would be kind of like if we had some sort of mass that was anti-gravity, right? If you had anti-gravity and you let go of an object in a room where gravitational field was down, which way would you expect it to go? Up to the ceiling, right? It's the same type of deal here. Okay, here in this particular case, which way is electric field pointing? Electric field is pointing there, right? Technically, actually, that way in the picture, but yeah. So a negative dropped here should do what? Go up. Yeah, go up the opposite. All right, we talked about this yesterday. If you got two charges, you can do potential energy on the right. If you have a charge and you're just looking at an empty space, you're doing potential. What we talked about the other day is how many. Let's knock out all of them because I think the analogy is great for you. If I have two masses, can I have a force gravity?
Yes.
Yes. If I have one mass, can I have a force gravity? No. Can I have a gravitational field?
Yes.
Yes. So think of it basically, two masses gives you a force of gravity, one mass gives you a gravitational field. If I have two charges, can I get a force electric?
Yes.
Yes. If I have one charge, I cannot get a force electric, but I can get a electric field. Correct. So continue this analogy. If I have two charges, I can get a potential energy. Right? If I only have one charge, I cannot get a potential energy, but I can get a potential. Remember, the potential is a single location. Voltage is a potential difference between two spots. So the correct wording here is that this location is just a voltage. It's a spot on the scale. You're not going to get a potential difference until you look at that location, and then you also look at this potential right here. Would be R1 in that case. Once you have both of them, you find the difference, and this difference right here, this guy right here is the amount of joules per coulomb if a charge goes between these two particular spots. All right, I'm not going to worry about that right now. We got other stuff to do. I want to get to stuff. Okay, potentials and charge conductors. Okay, some basic stuff here that this is kind of new for, but it's also pretty easy. If you're talking about charged conductors like we did before, okay, what is a charged conductor? I'm sorry, you get electrons on a metal. So let's bring out the electroscope. I put electrons on this. Let's remind ourselves of the rules of conductors and electrostatic equilibrium. For starters, where's all the charge going to go? You need to be more specific if you're talking about three-dimensionally speaking. Where's it going to go? Is the negative in the middle of that right now? No. It's definitely, so that's what I was looking for you to say a second ago. Number one, it's on the surface. Number two, what you want to think about is it's evenly spaced out, right? They push each other so that they're evenly spaced out. So would you expect any of the charges that are on there to be moving? Now I say in air quotes, moving, because you're probably not wrong that they're moving, but when we talk about moving in electrostatic conductors, it's like talking about when you guys, if I trap all of you guys in the corner, and have you guys bounce around at random, and where should I find you eventually, and you're evenly spaced out, Are you still moving at that time?
Yes.
Yes. But if you're evenly spaced out, we would say you're in equilibrium, even though technically there are net forces on you because you're evenly spaced out. And so we would say in that case, in a big sense, that you're not moving. Does that make sense what I'm saying there? So charges are moving here. They're evenly spaced out. They're bouncing around in equilibrium. So, in other words, if you look over here on the slides, should it take any energy to go from A to B? They're all not moving. No. The potential difference between A and B in this particular case should be 0. Or the electric potential is constant everywhere on the surface of a conductor in electrostatic equilibrium. Means this has some V here, but that has the exact same V. So what's the potential difference between the two of them? 0. This is extraordinarily similar to the conversation the other day with the bird on the wire. The birds are just getting better and better. I mean, it's
That's
just,
a monkey.
it's, no, it's not.
Wings.
No, it's not. No, it's not. It's a bird. All right. Anyway, here, I'll show you. Okay, so the voltage on both feet is exactly the same. The potential difference is 0. The voltage between those two spots is exactly the same. It's in 0. Okay? Electric potential is constant everywhere inside the conductor, but electric field inside a conductor is 0. So guess what the potential is inside of it? 0. All right, let's talk about the electron volt really fast. Potential energy, by definition, is charge times a volt. Yes? A single volt is a joule per coulomb. An electron volt is when you deal with ridiculously tiny amounts of energy, and we're going to be using it a little bit later. So all it is it's the amount of energy to take one electron through 1 volt. So we equate it 1 eV. How do I figure it out? Well, it's real simple. How would you get the energy if you, of a charge going through a volt? What would you need? I have 1 volt. How do I figure out how much energy is going to go through it? I need to know the charge. Do I know the charge of an electron?
Yes.
So E is 1.6 times 10 to the negative 19th times 1. So 1 electron volt is 1.6 times 10 to the negative 19th times 1. So it's 1.6 times 10 to the negative 19th joules. All that is equating a very small amount of energy, because we're going to be dealing with electrons at times. So I could say, for example, instead of saying a ridiculously tiny number, like instead of saying like, hey, how much, excuse me, how much energy does this electron gain by going through kind of a 10 volts? Instead of saying, well, I could do the calculation, 1.6 times 10 to the negative 19th coulombs times 10 joules per coulomb, and ending up with 1.6 times 10 to the negative 18th joules, which doesn't make a whole lot of difference to me because I don't know what these tiny numbers equate to. I could instead say 1 electron moving through 10 volts is 10 electron volts. Now, are you going to be able to use electron volts with other types of energy, like kinetic energy? No, you are going to have to go over to joules to do that. But in a lot of cases, this will suffice and make things a lot easier to understand. An electron initially at rest accelerates through a potential difference of 1 volt, gaining kinetic energy, where a proton, also initially at rest, accelerates through a potential difference of negative 1 volt, gaining kinetic energy. So you'll notice in both of those cases that the electron had an increase in potential, because that's a decrease in potential energy, and the kinetic energy had a decrease in potential, because that's a decrease in potential energy. Which of the following relationships holds true? Should the kinetic energy of the proton and the electron be equal? Should one be greater or less?
Proton should be greater.
Agree, disagree? What do we think? Let's get a few answers.
Proton has a larger mass than an electron.
I would suggest writing a thing or two down for equations.
If an electron is going through a difference of 1v, a proton is going through a difference of negative 1v with the negative sign as well.
No, what you want to think of there, like I said, all that really says is that they're both going the correct direction, right? You remember that what we said before, a proton should decrease in potential in order to be going the right way, right? So it's just this. Here, I'll put numbers up here. Okay, if I put 1v and 0v, what we said is electric field is going this way, right? So what does a proton naturally do in its change? -1. What does a negative do in this case naturally in its change? +1. So they're both going, by saying this for them, that's not the answer. They're both saying they're going the correct direction. The answer is 1. Why? Well, just look at the math. Potential energy change is Q delta V. Did they go through the same potential difference? Yes. Do they have the same charge? Yes. So should they lose the same amount of potential energy and thus gain the same amount of kinetic energy? Yes. They all gain 1 eV. But you're not wrong. The mass of the proton is bigger. It's just their kinetic energies are exactly the same. What will be different if we take that amount of energy, this is the same, we take it over to the kinetic energy equation. Kinetic energy is equal to what? Let me ask you a question. Spainhour versus a sumo wrestler. Do they have to be going the same speed to have the same kinetic energy? No. Why? Inertia. Correct. So you are right. You've got a similar idea with mass. You were just in the wrong spot. What is different between the two of them because they have different mass? Speed, but yes, since we're talking about energy and speed. Yeah, the proton can be going way slower and is going way slower, but carrying the exact same amount of kinetic energy. All right. Let's talk about equal potential surfaces. Okay. Remember this equation right here?
Yeah.
So all of these equal potential surfaces are calculated from that particular equation. So if I put a particular Q in the middle and I look at a distance of R, I could plug the number in there, I could plug the number in here, and I could get a value. Okay? And I'm going to make up a value real quick. We're going to say this one, so this is positive, this is close, so this is going to be the biggest number here. I'm going to say 500 volts, 400 volts, 300 volts, and 200 volts. Okay. If we are talking like my empty hill analogy, what really helps to look at here is think of what you're looking at on the left side right here as a hill, the top of a hill. Okay? So what do those dotted lines represent if that's the top of a hill? No, the blue dotted lines. What is the blue dot? If we're looking at the top of the hill, if this is like kind of
It's going down.
what do the dotted lines represent?
The distance from the top.
No, that's true. Not what I'm looking for here.
So you're sloping down.
The dotted lines represent the same height. Where's the top of the hill? Where's the tippy top of the hill? Right here. Right? So what this dotted line represents is being a little bit lower on the height, right? So keep in mind then, if I were to walk along the dotted line, how much would potential energy change? None. Now, is it very likely, if there are no other forces involved, that you're ever going to walk that way? No. It's not very likely that you're going to walk along an equal potential surface. Which way are you probably going to go on this hill? Down the hill. Exactly. We would expect a positive to go this particular way. And notice with potentials, what does that mean? What is the potentials doing as you go down the hill? Decreasing. What would a negative do in this case? They would actually arguably go up the hill in that particular case, or potentials would increase. Yes.
So this is effectively looking at like that 3D graph we had earlier.
Yes, very much so.
From the top down.
Yeah, from the top down view. It's 100% right. It's 100% right. And this over here, those electric field diagrams, like we talked about, once again, these are equal potential surfaces, except all of these are now calculated with KQR from the positive plus KQR from the negative. So guess what this right here, guess what that potential is?
Zero.
That should be 0, correct. That should be 0. Over here on the right side, we have something like 500, 400, 300. I totally screwed up because I should have started at 400. It's all right. 200, and I'm assuming there's a 100 somewhere in between. Over here, what are these then? Yeah, there you go. And what do you expect a positive to do in terms of these numbers? What do you expect a negative to do in terms of these numbers? You get the idea. All right. Yeah, let's not worry about that. Let's not worry about these guys right here. All right, capacitors.
Xerography. I guess I don't want to
Look at it. It's cold enough today. Look at that. Hold and charge. All right, I'm gonna charge this bad boy up.
Win.
No.
Stole it.
It's my charge.
Go. Come on!
This reminds me of
That's
the
so
charge.
good. I even like that.
Do you want to take it? I just literally gave it some. I like literally touched it and it went, okay. Then I took it. All right.
Mr. Electric.
It happens periodically, by the way, especially when it is cold outside, and you know this because if you reach out on your car, sometimes you'll randomly find, or door handles, and you'll find a shot. You do pick up charge throughout the day. As a matter of fact, in the summer, you also do. It's just that there's so much wetness in the air, there's so much humidity that it's kind of like I've equated it before as kind of like when there's liquid in the air, when it's humidity, if you like. Okay, it's kind of like you can sort of imagine that like you are connected to everything by like a billion different wires. So like, would you ever expect to retain a charge in that particular case? No. As the water gets taken out of the air, it's kind of like removing wires until there's like a handful out there. So will it take your charge? Eventually, but not nearly as quickly in this particular case. Which means that, for example, when you move next to your clothing, you have hair on you. You're mammals, you do. I'm sorry. Okay? Your clothes are very much like are very much going to probably steal some of that. You're charging by friction, especially when you have longer sleeves and there's more surface area, specifically between you and your materials. So a lot of times through that and talking and putting your hands on other people, you will in fact pick up a charge. For me, doing these examples, a lot of times in Physics 1, I do them like all day long when that happens. I'm in Physics 2 and Physics 1, and all day long. Sometimes I even get a chance to do them on IPS. Like towards the end of the day, I'll reach out and touch it, thing doesn't move. Thing doesn't move. What does that mean if it doesn't move when I touch it? I'm the exact same charge. I am the exact same charge. So what you'll see me do then, potentially, is I'll just start walking around the room doing this, touching as many metal objects as possible, hoping to remove some of that charge, and then I'm actually a little bit better at my examples in that particular case. All right, so I'm going to wind this bad boy up, but I'm going to try not to get it to spark. Okay, because right now, what could we say? Well, actually, before we let let's spark. Let's go back. Okay. Let's talk about a very practical use of potential and potential difference. Okay, I want you to be able to see these things in a very practical way, in a way that makes sense. Right now, what is the potential of both of these? 0. Okay, meaning why are they 0? Like, what can you look at to tell you they're definitely 0? What? Not why. Why? What can you what simple thing can you look at?
Both neutral.
Both neutral. Correct. In a very practical way, think of like if it's neutral, like this table has positives and negatives. So if I want to look at this area, all those positives are trying to cause an electric field pointing this way. But it's neutral because it has an equal number of negatives. So if all of those positives are pushing this way, then an equal number of negatives are pushing this way, and so what's the electric field do? Zero, meaning there's no force on a charge here. So if there's no force on a charge, are we possibly going to do work? No. In order for work to happen, you need force and effort to go some displacement. So when we say it's got a potential, really it's a direct connection, like I said, to electric field, which we start to understand. Okay? So I wind this bad boy up, but I don't spark it. Now what's happening here? Remind me what the Wimphurst is doing.
Charging one side positively and the other side negatively.
Yes, pulling negatives from over here, making that positive, and now there's negatives over here. So right here, what is the technical direction of electric field?
What side's positive? What side's negative?
This one's negative, this one's positive. So it's going this way. Yes, there's an electric field this way, which means that there's a potential force on a charge in the middle. Now, why is there no spark? Why is there nothing transferring right now? Air is a insulator. It holds on to charge really well. It puts its own force on it, holding it in place. That being said, is there still right now, am I going around? Yes. Is there still the possibility of force and energy coming out? Yes. So while there's electric field, we would also say there is electric potential. Okay? The potential difference roughly between them right now, actually I'm going to do it just so that I can see what it is, and I'll tell you how I just figured that out. It's about 5,000? Yeah, about 5,000 volts. Okay, so right here, check it first. About 20,000 volts. Okay, the way that I'm doing that, the way that I'm figuring out that number pretty quick, is we have calculated, and technically this number is different for every single situation. I don't know this for 110% fact, but air has an electric field. The necessary electric field to break through air is 10,000 volts per centimeter. Actually, what I should probably say is,
Should we write this one down, or is this just kind of for fun?
yes and no. 1 million volts per meter when it actually cracks. Now, how did I do this? Well, remember, voltage was defined as electric field times distance. So electric field is a measurement of voltage per distance. Okay? In other words, the stronger electric field means we have more potential energy per distance. And doesn't that make sense? Right? Technically, as I'm winding that thing up, what I'm doing is I'm increasing electric field. Right? I'm increasing the voltage per distance. And when this happens, that's when we get a crack of energy. So when I said 20,000 volts, I'm estimating in my head, I'm looking at that thing real quick and going, it's about 2 centimeters apart. 2 centimeters apart means it's at 20,000 volts. How are we doing with that? Okay, now, answer me this, because it's very important for the next thing. Assume that I charged it enough to crack at 2 centimeters. I don't know if I did or not, okay? Because it's hard to see. I kind of have to actually experiment. That's about 1,000. This is about 10,000 volts, okay? But assume that we got a number that gets to 20,000 volts. What does 20,000 volts mean between these two?
Distance was 2 centimeters.
That's not quite what I'm looking for. Well, just in general, if I said there's 20,000 volts between these two spots, what does that mean? Or I'll help you out to kind of put this in terms. There is 120 volts between these two spots. What does that mean? What's that?
For every coulomb that goes there, it does 20,000 joules.
Potential for how much energy if you drop a coulomb in. 20,000 volts if you drop a coulomb in. Why am I not afraid of you getting hit by this, even though there's 20,000 volts here? 20,000 joules definitely going to screw you up pretty bad. So why am I completely fine with you getting zapped by this if it's at 20,000 volts? What's that? Not quite. What's that?
So our charge is neutral or close.
No, that's not what it is. There's 20,000 volts between this two spots. It means if a Coulomb passes from here to here, it will put out 20,000 joules.
We are not a conductor.
Not quite. You're very much a conductor. As a matter of fact, your skin is the only thing that is not a conductor. You are made of a bunch of canals inside of you that are like pretty much all water, and actually water that has a bunch of minerals in it. You can conduct electricity, something serious, if you can get through the skin. The only skin it's not. For the most part, you're a conductor, not a conductor. But in this case example, you're a conductor. You're fine, especially at 20,000 volts. So what is it that protects you? The fact that 20,000. Why?
Just like with the birds.
No, it's not the birds example.
Okay.
If there is 20,000 volts between here and here, okay? I'm sorry, there wouldn't be at this distance. At this distance, I'm roughly at it's about a meter. Okay, so it's 1,000,000 volts. If there's 1,000,000 volts and there's a crack of lightning between there, okay, I'm gonna get zapped, certainly, but I'm probably not gonna die. I'm probably gonna be okay, okay? But 1,000,000 joules would definitely kill me. So why is this situation, 1,000,000 volts, not equating to 1,000,000 joules?
It's got to do with the per coulomb.
Yes, it does. Very much so. Do we usually transfer a full coulomb of charge? Coulombs are freaking-gantic. There is a huge amount. It's the exact opposite of what you told me exactly. Yeah, it's a small amount of coulombs that pass through. If I have 1,000,000 coulombs, but I only transfer 4 nanocoulombs of charge through it, do I get 1,000,000 coulombs out? No, as a matter of fact, calculate it. Well, how much energy are we getting out if I said 1,000,000 volts, but you only get 4 nanocoulombs through? Actually, I said nano. Say micro instead. 4 micro.
-6.
So 1,000,000 volts times 4 microcoulombs. How much energy you got coming out? 4 joules. Not much. Now, the whole purpose of this was to show you this. This device over here, when I crank this and I separate charge, what you can kind of think of it doing as it's kind of it kind of stores energy. Okay, it stores energy, and then I can release the energy if I just let it get close enough, and there goes the energy. That's what we're dealing with capacitors. Okay, a battery, for lack of a better word, and we're going to talk a lot more in detail about the battery next chapter, so I'm just going to give you a very basic sense of it right now. Okay, a battery it's that empty hill, but something inside of it, the chemical reaction, enforces that long term. Like it keeps making there be a difference, right? So this battery, for example, being 12 volts happens because it separates the charge. We'll talk about how it separates the charge. So if you just think of a battery in general, separates charge, takes the negatives from one side, puts them on the other. So this side's positive and this side's negative. Now, I hook it up to 2 metal plates. These 2 metal plates, what happens on this side if positive is hooked up to a neutral metal plate?
Plate loses electrons.
Plate loses electrons, therefore becoming positive. And this side over here gains electrons. Okay, so you'll notice, hopefully, what we're describing right now is literally that thing right over there. Okay, and this side gets negative Q. Now notice we're using a capital letter in this particular case. And the other thing that you want to think about is how are these two amounts going to relate? They're going to be equal and opposite. So in total, how much charge is being stored? None. There's no charge actually being stored in a capacitor. Now, that's kind of a little bit weird because, yeah, there's actually charge being put on one side and charge being put on the other. Okay, and then we take this area right here, okay, and we take this distance right here. Consider that when we talk about this next piece right here. Capacitance is defined as how much charge you can store for a certain amount of voltage. So if you take the voltage in this case would be the voltage of the battery. The charge is right here. What would the units of that be? Well, it says it right there. What do you got?
Coulomb per volt.
Coulomb per volt. Similar to always, science is like, we don't want to take coulombs per volt all the time. Let's pick a famous scientist and give him his dues. So they actually call them 1 farad. This is also known as a farad, not a farquad. So when you see farad, you should think coulomb per volt. And as always when we do this, and I tell you a ratio, the hope is that what you see is more than likely what's going to come out of this is the following. I rearrange it to this equation right here, and what I can see here is, all right, if I look at a capacitor, and a capacitor says that it's 3 microfarad. By the way, micro is quite frankly the most common actual SI subscript on these. It's almost always that they're in micro. If you see a milli, we might have one in the back. I'll show you one in just a second. But if you see a milli, they're gigantic. They're ridiculous. They're almost always micro ones. But if I say 3 microfarad, what I'm saying is that that capacitor for 1 volt stores 3 microcoulombs. Volt per coulomb. So if I have 12 volts, okay, so if that's for one of them, multiply by 12, I can store 36 microcoulombs on that particular capacitor. Does that make sense? Now, the question, of course, becomes, why? Why are we storing charge on this particular capacitor? Why do we store charge on that capacitor? I'm sorry, Wimshurst machine. The Wimshurst machine is a capacitor. Why do we store charge on it?
In order to have a.
Let me give you another example through the Wimshurst machine. We're losing him. Clear. Defibrillators are an example of a capacitor. Okay? Capacitors are used on a ridiculous amount of electronics. The most common of which that I could probably say quickly, but only for so much longer because they're almost virtually non-existent anymore. A camera, like an actual camera with a giant flash, needs a huge amount of burst of energy. That camera doesn't need it doesn't need that burst of energy always. It just needs it at one particular time, and it needs it very quickly. Capacitors are basically temporary batteries. You charge a capacitor via a battery, and if a battery is like this continual process of separation of charge, if we go back to my analogy, it's like some engine throwing kids on top of a hill. All right, like separating these charge so these kids can roll downhill continuously. A capacitor is, all right, let's put these kids on a hill and roll them all down really quick. Capacitors are used for large amounts of energy very, 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 very quickly. All electronics use capacitor, and if you don't believe me, take your flat screen TV at home and try to turn it on and off very quickly. You used to be able to do that with CRTs, and they go on and off and on and off and on and off. You cannot do that with current technology TVs. Why? Because when you turn it off, it requires a huge amount of energy to turn back on. So guess what its capacitors are doing when you turn it off? They're using the voltage in the wall to store charge.
Does that have something to do why TVs, when you put your hand against it, doesn't get the little staticky feeling anymore?
That's every single TV. You can literally do it with this one too, and that's just because the reason why these are charging is that electrons are hitting them, and so this surface is very much charged. And by the way, your answer to your question, the staticky, is that the charge that's up here, going back to last chapter, is polarizing your hand. It's literally just that this screen is probably negative right now, and it's pushing the negatives out of my hand, leaving positives nearby, leaving my hand with a very tingly feeling right now because it's setting off all the nerves in my body, because my nerves are meant to show me when something hits them, and all these negatives are running into them continuously, and so they're going, I can feel something right now, even though they're not actually touching anything. All right, so the purpose of a capacitor is essentially to do energy. Now, if you think of a battery like an empty hill, for the purpose of getting energy, what you want to think of always is, well, actually, I'm getting ahead of myself, I think. Let's talk about how we can make a capacitor better. Well, a capacitor better would store more charge. And what did we say? What is this positive doing to this plate over here?
Literally keep grabbing this like it's I'm trading these back and forth.
What is the positive side doing to the neutral plate?
It's positively charged.
How?
Taking away electrons.
Taking away electrons, correct? So the thing is, as it takes away electrons, this area becomes positive. Takes away more electrons, you get a little bit more positive. But what are these positives going to do to each other?
Repel.
So they're going to spread out, right? Okay, they're going to spread out. Now eventually, you're going to keep pulling, you're going to keep pulling, you're going to keep pulling, and you've pulled so much off of that, that what is this positive going to do to the negatives being pulled off?
It's gonna keep them.
It's going to pull back, right? It's going to pull back, okay? And same way over here. What happens to this plate?
Gets incredibly negative.
Gets incredibly negative as the negatives flow onto this right here. Now, what are these negatives going to do to the negatives coming in as it gets more and more charged? Push back. So eventually, this is going to push back as hard as this is pushing. And that's going to happen, if you think logically about it, this makes sense, when this voltage is the same as this voltage. This will be, so this, why is it getting more and more voltage? Because we're storing more and more and more and more charge. When does it stop storing charge? When this is pushing back on these charges the same way that this is already pushing on those charges. It's kind of two equal people going back and forth here. So, how can we store more charge? I'm not going to worry about that right now. Okay. Yeah, electric field goes back to the Gauss's law. Actually, it's not a bad idea to talk about. Gauss's law, if you'll remember, gave us this, that the electric field of something is equal to charge density over that. So the more charge density we have, the more electric field between these two particular plates. And the voltage between these plates. By the way, I want to point this out. Notice that this setup is literally what I described as the setup for getting a uniform electric field. This is how you get a uniform electric field. I just didn't give it a name. Now I am. It's called a capacitor. Okay? So we get more electric field, essentially. All this says is more electric field by storing more charge. And if we have more electric field at a certain distance, okay, we get more voltage. If I have the same electric field and I increase distance, what should happen to voltage? The same electric field, and I increase the distance. That's just like saying I have the same gravitational field and I did what to the hill?
Oh, makes you
It's taller, yeah. So what just happened to the voltage stored? Increased, absolutely. Now, what can I do here to say, let's say, what could I do to store more charge? Well, if I wanted to lower the density, okay, if I wanted to lower the density to allow more charge on, but I've got so much charge on here, what could I do to lower the density?
Increase the area.
Increase the area. Or another less fancy way of saying that is I just gave it more room to spread out, right? So if I give it more room to spread out, now more of these can continue coming on here. Okay, and when that happens, yeah, I don't love this one entirely. Let's just explain this in a more basic sense. One, how can I store more charge? The first thing I can do is increase area. What's the other thing I can do? Well, watch this. I said earlier that these negatives here, okay, are being pulled over by this positive, yes? And this positive is attracting it back. These negatives, though, aren't in a vacuum. What are these negatives going to do to those negatives? Repel them. What would increase that force?
Lesser distance.
If I made them closer together, I could push more charge off of there. And vice versa. What are these positives doing to these negatives? Pulling them on. And if it's closer, I would pull more. So having more area should increase the amount of charge I store for the same amount of voltage, and the distance decreasing. I'm literally writing what they're about to write. There it is. That little letter right there, you'll remember this came from epsilon naught, came from Gauss's law. And what they're essentially trying to show right here is this. Capacitance is equal to charge over voltage by definition. We showed up here that charge is just charge density, charge per area, times area, right? So I replace Q with charge density. Voltage is equal to ED, right? And E is equal to density over epsilon naught. So if you plug it in here, these densities cancel, the density don't matter, and you're left with that equation right there. Again, simplistically put, what this tells you is, hey, if you want to make a capacitor, what do you need?
Some source of the like that.
A battery will charge a capacitor, but no, that's not a capacitor. What is a capacitor?
Uniform electric field.
Like, how would you, like, literally, what objects would you go out right now and get if I said go make a capacitor?
Distributor.
Two metal plates.
Distributor? Sorry, I
A
was thinking
source
about
of
my car.
taking away
Two metal
electric
plates.
field.
Literally 2 metal plates will create a capacitor. How do you make a bigger capacitor? You have 2 ways. What are they?
Charge the plates somehow.
You make them closer.
You make them closer, and you make them bigger. Now, what's the problem, though? So this will give us more capacitance. But what is the problem with getting 2 plates too close together?
Well, that.
I want to store more charge than that. But what's the problem? They're shocking across. So there's one other thing that you can do to really help yourself out on this matter. What you do, so there's the uniform electric field. We talked about that already. Yeah, okay, capacitors are used for all sorts of places. I'll come back and talk about that in just a second. Oh, shoot.
Oh no.
That's the next chapter, right?
No, it's not. It's 100% this chapter. I forgot we had to do all that. I won't do it right now. I'll push the test another day back. I don't love that though. What I really wanted to get to was darn it, we're not even getting. Why are you not getting to? There it finally is. That's a weird order. Okay. The major way to make a better capacitor is use what's known as a dielectric. A dielectric is a fancy word for a very simple thing. A dielectric is simply an insulating material that you put between the other 2 plates. And the reason it works is twofold. Number one, the fact that it is non-conducting means you can get those plates a lot closer together and they won't shock nearly as much. They won't shock nearly as quickly. That's the first. You can make the distance smaller. But the second thing that's going to happen is, what does a insulating material do in an electric field? For example, this screen is very negative. I said it earlier. I have a non-conducting-ish. I know, that's a weird thing. I go back and forth between talking about human bodies as non-conducting and conducting. They're both. Okay, I bring it close. I am in an electric field. By the way, this is negative-ish. So which way is the electric field? At it. So I put my hand in an electric field. What does my hand do? Last chapter. Okay, I got you. There it is. I put a charge. I put a material in an electric field. What happens to it? It polarizes. Correct. So, why is polarization going to help? Well, let's look here. What are these negatives going to do to negatives nearby? What are these negatives going to do to the negatives in the material? Push them away. So we're going to get negatives all the way over here. And of course, what's going to be left here because the negatives just left? Now, it's not actually moving through it because it's an insulator. But what are these positives now going to do to negatives in the wire?
That's right.
It's going to pull them on. And what are these negatives going to do to negatives in this wire? Push them further away, making this plate more negative and that plate more positive, meaning for the exact same voltage, we have increased the overall capacitance of the material. The best way to look at that is simply this. You take the equation that we just said,
Be quiet.
and you add another constant. And my apologies, that's not a K, that's kappa.
Thank you so much.
That's
Okay. All right.
Okay, but how do we write it? Like a K?
That's just
Oh,
a
fancy
shame.
cool.
That's just
All right.
early
Now,
days.
let's break down that conversation. Let's break down that conversation in a very simple way. Okay? What did we say? What's the purpose of a capacitor? Well, the idea of it is you store charge. You move charge from one side to the other. The inevitable purpose is to let them discharge, to let this positive move over. Let this negative move over to the other side. When it does, as we see over here, as you see with the defibrillator, as you see with every piece of electronics, when it discharges, it releases a huge amount of energy. So yes, the purpose of a capacitor is having opposite plates that store energy. It also creates a uniform electric field in the middle of it. How can we make a better capacitor? We can make a better capacitor by increasing the area, decreasing the distance, and using a dielectric. Now, usually, by the way, if you've ever recognized a capacitor, you might think this seems weird, because you might be like, I have never seen in any piece of electronics ever two giant plates like this sticking out. It seems like if you need a lot of area, this would take up a lot of room. And you're right. So they put an insulator in the middle. They put a dielectric, which A, lets it get them closer, really close to E. B, by itself increases the capacitance. But C, they keep going with it. They wrap everything in this insulator. And then what they do, if I look on the very end, is they Swiss roll this beast.
Swiss roll this beast.
Okay, in there, all next to each other, because they can then store a huge amount of area in a fairly confined space. And for those of you that have ever looked inside of electronics, what shape is a capacitor? It's a cylinder. That cylinder, if you open it up, is just two flat plates Swiss rolled together so that it doesn't take up a ridiculous amount of room. And if you want to have a larger capacitor, guess what happens? It either gets thicker, meaning area gets bigger this way, or it gets taller, meaning area gets bigger this way. Because honestly, when you have that insulator in there, you smack those things closest together as possible to make this ridiculously tiny. Usually, depends. They can mess. You can see right down here, all these different kappas right here are are used for, on all over the place. Usually, they use some oil, like a silicone oil, like this one right here. But that's pretty. They're going to use like a cheap material that they can use for that. They can find relatively easily in order to be able to use, and they put that whole thing in oil, and there they go. That's a capacitor. Now, I don't like the order they do this in. The whole purpose of this was energy. The whole purpose of this was storing energy. Okay? What's our normal equation for energy if you have a voltage? Boo. You have a voltage. How do you get energy? What's the equation?
Oh.
There it is. Energy is just, remember, if you struggle with what I just said, voltage is joules per coulomb. So how do you get joules? With joules per coulomb.
Multiplied by Coulomb.
So the coulombs cancel out and you're left with joules. Now, this equation only works if the voltage stays constant. the thing that is creating the voltage in this thing is the actual charges. Stop it. Go. Good. What are you doing? I want to leave. What? Oh, I see what happened. I screwed up. All right. So, in other words, I hook this thing up to a battery. So, battery for right now. Okay. Bump is what charge? Positive. So I start here. They're neutral. I'm going to do this really darn slow. Okay. What happens is, okay, this thing will add an electron. This thing will take away an electron. Add an electron, take away electron. Okay, and so on and so forth. And what we said, again, was that this will stop when the voltage between these two plates matches the voltage of the battery. The way a capacitor is used is then you've got these two sides hooked up to some other, like, electronics. I'm going to not get very specific with this. Okay, and right in here, there's something called, and we'll talk about this more in circuits, a switch. And so you press a button, literally, or something like that, to close the switch, which allows the negative through the electronics and over to the other side, so that it fully discharges, releasing all its energy. But with a battery, you can use this equation, and it's not a problem because that voltage is staying the same. But watch carefully here. This voltage is only because the charges that are here, right? So let's say you disconnect it, you were discharging. What's going to happen? I'm going to, again, go in slow-mo. This negative is going to move through over here to make those both neutral, right? What just happened to the voltage because one negative just went through? What just happened to the voltage between these two plates since there's less charge?
Decrease.
Yeah. If you want, this is the worst analogy ever. It is. I'm sorry. But it works. Capacitors are an empty hill made out of kids. Okay, so imagine you've got, I know, I certainly shouldn't have put myself on tape saying that. All right, so here's the hill. Okay, so here's the hill, or here you go. This kid is holding up the slide for this kid over here. Now, this kid goes down. They release energy, right? But what just happened to the size of the hill? We lost a kid, so now the hill is smaller. I'm sorry, not kid, child, Coulomb. We'll say here. Let's do this for the sake of the video. We're not going to use kids in here, guys. Okay? The kid's name is Coulomb. Okay. All right, so we're going to use coulombs correctly. All right, so you've got coulombs stacked on top of each other that are creating the size of the hill. So when the first Coulomb rolls down the hill is now smaller. Meaning, what happens to this number as the first Coulomb goes through? It gets smaller. So are you going to get as much energy now out of the second Coulomb? I don't know why I'm saying it like that anymore. I'm actually legitimately talking about coulombs now. Yeah.
Does Coulomb have a family?
No. I mean, hypothetically, no, for the sake of my example. I mean, no. What are you talking about? Coulomb is just a unit of measure of amount of charge.
He was a scientist.
It's 6.25 times 10 to the 18th electrons. I mean, or protons. All right, now, what this means. Watch. Okay. What this means is right here. Okay, this is what they're trying to show. Shh. All right, so the amount of work done is negative, because this is just potential energy, right? Blah, blah, blah. Okay, is the amount of charge, the total charge rolling through, times the voltage. But right here, the work that is done by the first Coulomb is the maximum. But as that Coulomb goes through, now the hill isn't as high, right? So now the amount of work being done is a little bit less, and a little bit less, and a little bit less. Now, that, you can sort of think of it like this if you look at this line. The maximum amount of energy coming out is going to be Q delta V, where Q is the total charge, and delta V is the total voltage, right? What is the minimum amount of energy coming out? 0. Correct. So instead of like looking at this as like this weird slant, let's look at it as an average. We'll take the maximum plus the minimum and divide by 2. So watch here carefully because people screw this up every time. This is your normal equation. That is almost always going to be your equation. And that equation works when the voltage is constant. But what I'm about to show you up here, this equation here, this is how much work is done by a capacitor. And notice it's the exact same equation. It's Q times delta V just with the 1/2. So just answer me this, write it down in your notes. I don't know what it takes to remember this, but this is the one thing I don't want people to screw up on this next test. When do you use the 1/2?
Whenever you're using capacitors.
Yes. When do you not use the 1/2?
Everywhere else.
Yes. You'd think,
I'm about
as much effort as I'm putting into this and have done for the last like 3 to 4 years, that this would not be an issue. But I will see 1/2 appear. Like, why is there one? There's no capacitor around anywhere. This is simply the amount of energy. Now, I can also do this in a couple of different ways because, so the last thing we do today, I will finish the capacitor stuff because I remembered how much was in that. I thought that I could finish today, and I'm not going to be able to because of that. But so here we have the amount of energy. I'm going to use that color. Here we have the amount of energy stored in a capacitor is 1/2 Q delta V. Notice, by the way, I'm somewhat using delta U and W interchangeably here because, honestly, who the heck cares about the negative? It's just a magnitude, how much energy is going to come out. But if I said, okay, if you said to me, all right, but how do I figure out, I've got a battery here, I've got a capacitor, how can I figure out how much energy that I'm going to be using? Well, what it really depends upon is the size of the capacitor. So watch here. Capacitance is equal to charge per voltage. What is capacitance controlled by? What equation? Simplest one. Now, the only reason I'm bringing this one up here is this. Okay, this one is controlled by how it's made. Okay, this is an important point of interest here. Okay, this one's controlled by how it's made. You control the area, you control the distance, you control what it's in. Then the capacitance is set. Now watch this because people screw this up all the time. I come here to this equation. I want to figure out how much charge is being formed. So I hook it up to a battery, let's say a AAA, so 1.5 volts. Actually, I'll use 2 AAAs, so I can just use a total of 3 volts. I hook it up to 3 volts. Then I hook it up to a capacitor. That capacitor is 6 microfarad. Okay? Using my equation up here, I should get charge is equal to capacitance times voltage, or 6 microfarad times 3 volts. Watch this because it's going to help you out a lot moving forward. How much charge is stored? Don't worry about this micro. Literally go 3 times 6. It's 18 microcoulombs. If I then change the battery, I hook up 2 more AAAs, which is pretty common to have 4 AAAs in a device. I mean, your calculator does. So there's 6 volts. Yes, your calculator is controlled by 6 volts. If you fair enough, you've defeated me. All right, you change the battery. Do you change the capacitance? No. This is what people screw up all the time. They look at this equation and they go, oh, well, if I change the battery, then I change the capacitance. Capacitance stays the same based on that equation. So if you change the battery, what actually changes here? You're pushing harder. So what should change here? More charge.
That's because you took distance. What?
The capacitance is set by what it physically is. Its area, its distance, its dielectric. You make it, you set it to the side. You go to the store, you get a capacitor. If you've got a capacitor, okay, then you're not going to be able to change that. If you change the voltage, you do not change the capacitance, you change how much charge is on here. You change how many kids, coulombs, are on the hill. Why? Because you were pushing harder with a bigger hill, so you can store more kids, coulombs. All right. Now, come over here. I make the battery bigger. One thing you got to be careful with this is this. Will making the battery bigger store more energy? Yeah. I go, oh, Spano, how much bigger will it make it? Well, you go, oh, well, voltage here double. So energy should double. No, it should actually quadruple. How come? Because doubling the voltage for the same capacitor also doubles charge. Now, if that's hard to see, we can make it a little bit easier, and this is the last thing we'll do today. I'm simply going to take this equation and do some substitution in here. I've already done the algebra with this to show you that Q is equal to C delta V, right? So if I plug that in here, what I can get is a new equation of 1/2 C times delta V times delta V, giving me 1/2 C delta V squared. Now, if I say the capacitor stays the same and I double the battery, you can see from this equation, oh, that means energy goes up by 4 times because that stayed the same and that needs to be squared. The reason that needs to be squared is because both voltage and charge are both doubling. There's another one, though, to look at here. There's one more equation that I'm fine with you using, and that's this. What if I solve for delta V here? So if I take this equation, which was originally this equation, I should get delta V is equal to Q over C, yes? If I substitute that in here, hold on, I'm going to highlight all of the equations that you're going to want. If I substitute that in here, I get 1/2 Q times Q over C. Or, in other words, the amount of energy stored is 1/2 times Q squared over C. These equations will allow you essentially to just kind of look at what numbers you have and what's staying the same. And I could now say, hey, capacitance is staying the same, charge doubles. What effect does it have on potential energy? In this particular case, the answer is it actually quadruples it. If I say charge stays the same, the capacitance doubles. Okay? What's going to happen there? Well, if charge stays the same and capacitance doubles, actually energy should cut in half. Correct.
What was the very top one again?
The first one that you need,
Okay.
the 1/2 Q delta V squared.
Yeah.
And again, I want to say this. This is your normal one. Normal capacitors. Can you tell I've had issues with this on the past?
Yeah.
All right. Bye, Morgan.